let's make a start. Thanks everyone for joining us today. So welcome to the Machine Learning and the Prediction Modeling Seminars. This is hosted by the Prediction Modeling Group here at King's College London at the Department of Biostatistics and Health Informatics. So we run these seminars monthly, and today we are very lucky and happy to be hosting a talk by Mizanur Khondoker. So he was previously part of our department as a BRC lecturer for 6 years, and now he's an associate professor in medical statistics at the Norwich Medical School at the University of East Anglia. He's an applied statistician, and he has a core interest in dementia research that's being focused on identifying early biomarkers and risk prediction and prevention of dementia. And from the methods side of his career and expertise, he's an expert on machine learning, on analysis of high-dimensional data, and particularly data arising from high-dimensional from electronic health records, and also using modern bioinformatics, genomics technologies, and also other areas of interest on statistics like latent class analysis and growth mixture models. So today, Mizan is going to be talking and showing us a performance comparison using a simulation study of dynamic prediction based on joint models and landmark analysis. I think this should be of very big interest for most of you. We are very happy to have you with us, Mizan. So thanks very much for accepting our invitation. And just telling to the people that this will be recorded as every time we do. If you would like to be added to our email list to be informed about this seminar, you can just type your email address on the chat, and I will add you to the email list. And also that if you have any comment or question, I'm sure that Mizan will be happy to answer them and discuss with you about any aspect of his talk by the end of it. So I think that's everything I wanted to say. So I leave it with you, Mizan. Thanks very much.
All right. Thank you, Raquel, for the introduction. And thank you all for coming. So as you can see from the title, I will try to talk about, I will try to present some results from a simulation study comparing the prediction performance of two methods of dynamic prediction, namely joint models and landmark analysis. I'll be using bootstrap simulation for the comparison, and I will explain during the talk the rationale for choosing a bootstrap simulation method. And to be honest, this is purely a methodological exercise just to see which method performs better in simulated data. There are a couple of technical slides, but you should be able to follow even if you're not familiar with mathematical details of joint models, etc. Because I'll be using some graphical illustration as well of the mathematical formulas. So this is a brief outline of what I'm going to talk about today. I will start with a brief introduction to clinical risk prediction models. I will start with an example of conventional risk prediction model for cardiovascular diseases, and also initiate the motivations for making use of longitudinal predictors in dynamic prediction. I will then give an overview of two methods for dynamic prediction, two popular ones for dynamic prediction, namely joint models and landmark analysis. And finally, some simulation results comparing the prediction performance of the two methods in terms of discrimination and calibration. So as you know, discrimination and calibration are the two kind of popular criteria for comparing prediction models. So risk prediction tools for clinical outcomes can greatly aid clinicians with early diagnosis, cost-effective management, and primary prevention of many medical conditions. A good example is the Q-risk calculator that most of you may be familiar with. This is in context of the UK population. for estimating the cardiovascular risk based on people's kind of age, gender, ethnicity, blood pressure, cholesterol level, and so on. So this estimates the risk of developing CVD over the next 10 years. This is a kind of screenshot of the risk calculator. So if I import my personal data, age, gender, and my blood pressure, area, postcode, etc., I just black them out because they're my personal data. They're not necessary for you to know, but it gives you it gives me that my risk of having a heart attack or stroke in the next 10 years is 5.2%. So this is very kind of easy to interpret. Although not a dynamic prediction model, this has been tremendously useful for clinicians. I think this has been in use in the NHS, across the NHS since 2009. And they use it, doctors use it for day-to-day clinical practice, for example, to decide whether somebody needs a prescription of kind of cholesterol or something. So as I said, this is not a kind of dynamic predictor. So this use only current values of the biomarker, your current data, ethnicity, gender, as well as some of the blood measures for estimating the risk of risk of cardiovascular disease. So the conventional prediction tools, like the one I have just discussed, predictors are typically measured at baseline or start of the follow-up. Often can use the most recent value of the biomarker, but longitudinal information between the baseline and current time is ignored. So the traditional risk prediction models, like the one I mentioned, doesn't make use of any information in between, right? They either use the most recent measure or use the baseline data. So this is the main advantage of dynamic prediction model. So it can use the most current value as well as the history of the longitudinal measures. So this gives more information actually in terms of predicting the clinical outcomes. So, and this is how Ben Houligan defined dynamic prediction in context of time to event analysis. So it is defined as the computation of the predictive distribution at a certain moment in time, TS, given the history of events and covariates. So this has been defined in context of landmark analysis, which I will come back to later. So main advantage of so this has several advantages of a traditional conventional static risk prediction tool. As time progresses, as additional information is collected for the follow-up visit, the prediction can be updated as you get new data from each participant or each patient. And access to this updated risk may be very useful for making clinical decisions. For example, this can make clinicians to gain better understanding of the disease dynamics and also help making most optimal decision at a specific point in time. And this is just a graphical illustration of how dynamic prediction works. So the left-hand side of the red line shows the observation period. So this is from Devaux et al. A new publication actually available online. So the left-hand side is the observation period of data collection. So the line, different line shows the different biomarker, longitudinal biomarker, and time to event is also collected in this observational period. And the red line is called, in the language of dynamic prediction, this is called landmark. This is the last point of the observation period, is the final landmark. Landmark can be set actually at any time point, but usually for clinical reasons, if you want to use the most up-to-date data, the landmark will be the last of the observation. And on the right-hand side, this is called the prediction window or the time horizon. For the cardiovascular risk tool I mentioned, it used to be the 10 years. Time horizon is the 10 years. So this is the interval within which we are interested in predicting the risk of the event of interest. For example, cardiovascular disease, and the red line, this indicates the landmark time point. Now, dynamic prediction has gained a lot of attention in recent years. This is probably due to better access to longitudinally collected health information. For example, due to advent of electronic health record systems, and also easy access to mobile devices and different apps for personal health monitoring. We can personally collect lots of data about ourselves, right, using just a mobile device or our watches, smart watches and mobile phones and so on. So this actually, so longitudinal data is everywhere nowadays. So this makes this dynamic prediction is a very attractive method for risk prediction. Several methods have found applications in the literature for dynamic prediction. Joint modeling, for example, joint modeling, landmarking, and partly conditional modeling. These three are most commonly cited methods for dynamic prediction. I will give a brief overview shortly, but briefly, joint modeling is based on a very rigorous statistical framework because it jointly models the distribution of the longitudinal marker as well as the time to event process. But it is a bit computationally hard, computationally intensive. Landmarking approach, on the other hand, is easy to implement because it just is standard, like fitting a standard Cox model. But it is a bit less good in terms of kind of theoretical rigor. It is not based on a very strong theoretical foundation. And the partly conditional model is a bit is kind of in between in terms of the computational complexity. This is also a good one for dynamic prediction. So joint model is probably the most natural framework for dynamic prediction. So the joint model actually links two submodels to fully characterize the residual trend distribution. So a model for the longitudinal marker, which is denoted by YT in this talk, and a model for the time to event process, which is a kind of the solvable data actually. So you have a longitudinal data as well as solvable data, and the two distributions are simultaneously modeled. So in the longitudinal, in the most basic form of a kind of longitudinal basic form of a joint model, the longitudinal submodel is represented by a linear mixed model. So you can see that observed data, YIT, is represented as the true value of the biomarker plus an error. And the true value is represented using a regression model. Regression model on the in terms of the set of fixed covariate and the random effect, subjective is specific random effects plus the residual. So this is the most basic form. There are other kind of complex modeling that can be used as well. And time to event submodel relate the true biomarker with the event time process by a Cox-like regression model. You can see, you might have noticed that this is very similar to a Cox regression model. But this mu-IT here is a kind of unobserved data. So it is not a covariate actually. It looks like a time-dependent model, Cox model, but this mu-IT here is actually unknown quantity. So this is the true value of the longitudinal process. So that's why for estimating that model, you need to jointly model the longitudinal process as well as the time to event process. So this is why that is called a joint model. And this is just a schematic diagram of the joint model that I just mentioned mathematically. So on the left-hand side, this is a longitudinal submodel. The star represents the original longitudinal data, but this is not in the joint model. The original data is not directly used for prediction, so it is the smooth version of the data. If you feed a kind of linear mixed model or any other random effects model, you can kind of have a smooth version of the longitudinal process. And this smooth version of the longitudinal process is used for predicting the survival outcome. So this indicates the probability of having Alzheimer's disease. So this data come from a it's a hypothetical plot, but based on the idea of the ADNI data set. So here the time to event is the Alzheimer's disease, and start of the follow-up is the MCI. So you can see that as the mini-mental score actually decline over time, and it increases the risk of converting to Alzheimer's disease. So from a joint model, you can estimate actually both. You can estimate the longitudinal process as well. So this indicates the estimated part of the model. So you can predict MMSE as well as the risk of future risk of the developing Alzheimer's disease based on a joint model. So it's basically two-way model. And another advantage of joint model is that it is not only the longitudinal marker. One can use the other function of the trajectory as a predictor. For example, you can include the rate of decline. So if you take the derivative of the longitudinal process, you can get the rate of decline. So rate of decline can be used as a predictor as well in the joint modeling. One can use area under the curve as a additional predictor as well. So it gives an opportunity to use other values of the biomarker process, other measures of the longitudinal process as additional predictor, which improves the prediction quality of the time to event process. And so once a joint model has been fitted to the training data, so I just represent the data using the dn. So n is the sample size, and this is the data, actually training data, survival time, indicator of the event, and wi is a vector of baseline covariate, and yi are the longitudinal biomarker. So this is my training set. So once a model is fitted to the training data, dynamic individualized prediction can be made based on the joint model, fitted joint model, and the data. And the probability of survival of a new person I, at least up to the time horizon. So this is the time window that you want to use for make the prediction. And given alive at the time horizon, not the horizon, landmark point is given by this probability. You can see the probability of surviving greater than the time horizon, given that the person already survived until the landmark time point is given by, can be approximated by a numerical integration. So it depends on this theta hat represents all the parameter estimate from the joint model. So it depends on the data, estimated parameter of the joint model, the training data, as well as the given covariates, baseline covariate, and the history. So this is the history of the longitudinal marker. So this gives a kind of nice analytical framework to make dynamic prediction, and you can see the dynamic nature of this equation. So if you increase the follow-up, so you can increase the history of the biomarker, but you do not need to refit the model. Actually, you can use additional data to make prediction based on the model already fitted on the existing data. Right, so landmarking. So as I said before, the joint modeling is very methodologically sound, and it's a natural framework for dynamic prediction, but it is actually computationally hard. Because likelihood construction require numerical integration over multiple dimensions. So if you have more than one longitudinal marker, so each of the longitudinal marker will have one or more random effects, because you need a kind of linear mixed model for fitting the longitudinal process. So it increases the dimension of computational dimension. So it becomes very hard computationally once you have more biomarker in your model. and can be very intensive or infeasible for multiple dynamic predictors. So a flexible alternative called dynamic prediction by landmarking was introduced by Ben Houligan in 2007. So this is based on just a standard survival model. So this doesn't require any special methodology or any specialized software. Only thing it needs actually subsample of the data at a particular landmark time point. So you fit a standard kind of survival model like a Cox regression model, considering data at a given landmark point, and then you can use this model for dynamic predictions. So I'll be mainly talking about these two methods of dynamic prediction. Actually, one is methodologically rigorous joint model. One is computationally very elegant, efficient, but doesn't have a very strong theoretical basis. Just to see which one actually perform better, because the joint modeling has some limitations. So idea of the dynamic prediction by landmarking is that you pre-select a landmark time point, yes. It is usually the end of observation period, but you can consider other time point of interest as landmark. And select subject at risk at TS, which is the landmark from the original sample DN, that construct an adjusted risk set at this particular time point. And then use the standard survival model to predict the probability of survival up to time horizon. Typically, standard Cox regression model is used. So you can see that this is very similar to joint model I mentioned before, but this is not mu-IT here. This is the observed data. So this Y twiddle T will be the last observation carried forward, because original longitudinal data is not a smooth data. So joint model has the advantage of predicting this YIT, but for landmarking, you will be using last observation that you have in the model. And often time origin is reset to the landmark T minus TS, but this is not always necessary. Also, the vector of baseline covariate are included as usual. So this is very simple actually, landmarking. You just need to subset your data based on who are at risk at a particular landmark time point. So once a model has been fitted on the subset data, you can calculate the dynamic prediction. So this is the dynamic prediction by landmark analysis. So pi I on the T horizon given TS is given by this formula. So this is the baseline cumulative hazard of the survival function. And this parameter comes from the Cox regression model, fitted Cox regression model, and everything else is known actually here. And one simple estimate for the baseline cumulative hazard is the Breslow estimator. So once you fit a Cox regression model, you can use the baseline hazard Breslow estimator to estimate this baseline hazard. So quite very simple to get dynamic prediction based on landmark analysis. Several extensions. The method I have presented here is the basic one that use the last observation carrying forward. Is the basic way to do landmark analysis, but several extension has been proposed as well. So regression coefficient is not actually constant. It depends on time as well. But I'll be presenting data for only the basic landmarking approach. Just a literature review of what people done in terms of comparison previously. So using various functional form of the relationship between longitudinal and longitudinal model and the time to event process. The Rezupoulos et al. 2013 demonstrated that the joint model performs better than landmarking. So this is actually, this guy actually has a lot of actually publication on dynamic prediction and joint model. So obviously, it's not surprising that joint model perform better than landmarking according to this evaluation. And another author, this group actually measures that will compare joint models but versus partly conditional models. Though this is another method actually of dynamic prediction, which I'm not going to get into too much detail, that show that performance of partly conditional models are comparable to that of joint models, but PC models have a better computational efficiency. So again, this actually joint model is the most extensive, actually computationally most difficult to compute because it's very, very time consuming. And Suresh et al. 2017 compared joint model and landmarking approach in context of a binary kind of longitudinal marker representing the illness state model, and suggests that JM is likely to perform better when the longitudinal marker can be well characterized. Actually, the third, this paper actually doesn't lead to a general conclusion that one method performs better than the other, but what they say is that joint model will perform better is the model, longitudinal model is good enough to characterize the repeated measures. And they also said that prediction by landmarking may provide very good enough approximation if it is harder to estimate from the joint model longitudinal marker process. So, so I'm going to now talk about kind of why I have chosen the bootstrap simulation. So most of the method I talked about so far used a model-based data simulation. So if it is a joint model, shared parameter model, so they simulate data from a joint model. So so if you simulate data from a joint distribution, so it is not surprising. So it may be good for the joint model because joint model actually completely specify a data generation mechanism. Landmark approach, on the other hand, does not provide a complete data generation model because it doesn't assume a model for the longitudinal marker, right? So one may question that, one may say that this model-based data simulation may kind of give an advantage to the joint model because data kind of simulated from statistical model. So to overcome this issue, we decided to use bootstrap simulation. So it doesn't depend on a statistical model. So it's likely to be impartial to both methods. And bootstrap allows quantifying the correcting for optimism in the estimate of prediction performance. Optimism, one way to do optimism correction is by a cross validation, as you know. But I will show actually another method of optimism correction based on the bootstrap sampling as well. So I'll be using bootstrap simulation to compare the performance of the two methods. Now, in terms of the performance criteria, this is as usual with any prediction model. So you compare in terms of discrimination and calibration. As you know, discrimination is the ability to distinguish between subjects with positive and negative outcomes, sensitivity in other words, and to generalize, it is area under the curve that can be used to measure discrimination. And calibration measures the agreement between the observed and predicted outcome. So it is the residuals, mean square error type thing. For dynamic prediction, actually, the standard discrimination calibration measure doesn't work because it's a dynamic prediction. So here we'll be using an extended definition of kind of discrimination measure, which is called, one of them is called dynamic area under the curve receiver operating characteristics curve. So this is actually weighted average of the time-dependent area under the curves. And calibration is the expected prediction error for joint models, as well as landmarking implemented in the R package JMBase. Again, this is by Rezopoulos, 2016. So this is a Journal of Statistical Software paper. They illustrated the method. And I just implemented from this R package. And the data that I'm using for bootstrap simulation. So most of you may be familiar with ADNI dataset, Alzheimer's disease neuroimaging initiative study. So this study was designed to identify early biomarkers for Alzheimer's disease. So the sample size is not, whole sample is not 863, but I have considered only 863 participants who are diagnosed at mild cognitive impairment at the baseline, because I want to measure the time to Alzheimer's disease based on the NCI state. So NCI state is the kind of baseline for this data. And the participants are aged between 55 and 90 years, and the follow-up time, length of follow-up, and the frequency of visit varied during the course of the study. But initially, the visit follow-up was every 6 months for the first 2 years, and then on a yearly basis. So I considered data for up to 12 follow-up visit, and duration of data was, maximum follow-up duration was about 9 years. And the two outcomes was considered, the survivable outcome is time to conversion to Alzheimer's disease from the MCI state, and longitudinal outcome was the mini-mental state examination score, MMSE score. So has been collected over the duration of 9 years. And I have also considered some baseline covariate as well, so demographics, some of the behavioral data, smoking status, alcohol abuse, medical history, as well as apoegenotype as fixed biomarker. And in terms of joint model, joint model will consider these two survivable outcome as well as longitudinal measure as simultaneously as outcome measures. And this shows the kind of how MMSE actually score influence the risk of converting to Alzheimer's disease. So this is only baseline MMSE. You can see I've estimated the survivable function, survivable curve for several levels of the MMSE score. So their baseline MMSE level, not the longitudinal measure. You can see that. So higher MMSE is better. Higher MMSE means better cognitive functions. So as you can see, actually, as the MMSE score is get smaller, the risk of converting to Alzheimer's disease get faster. The people get converted to Alzheimer's disease very at a high rate. And people with the MMSE score of less than 9 is already probably have Alzheimer's disease, so which is reflected in this curve. So even at the baseline, MMSE seems to be a strong predictor of conversion to Alzheimer's disease. So if we can use the kind of longitudinal MMSE measures for prediction, this would be even better. So if you consider a risk prediction model for dementia, for example, so it makes sense to include the longitudinal MMSE score as a useful, as a predictor. And here is the profile of the MMSE measures, longitudinal. So I've been showing only the baseline data. You can see that the overall range of the baseline is not different. So these two panel shows the data these are the people who didn't convert it to Alzheimer's disease. So they are MCI, all are MCI, but they are non-converters to Alzheimer's disease within the observation period. And this guy has converted to developed Alzheimer's disease from the MCI state. And you can see the two very different profile actually. So this is almost parallel. The MMSE score is kind of stable overall. And here you can see the decline rate. So obviously longitudinal MMSE score contains useful information about the conversion to Alzheimer's disease. So risk model for dementia may benefit from using them in the risk model. And this is the fitted joint model on the data that I just mentioned. You can see there is a longitudinal process because there are two models. So this is the model for the longitudinal process, and this is the model for the time to event process. So this is something similar to a Cox model, given that this is a time-dependent variable. And this is the true, this is considered, this prediction of this MMSE comes from this model. So they're jointly estimated. So I have considered a quadratic model for the linear mixed model for the longitudinal part. You can see there is a time and time squared, and both are statistically significant. And in terms of the baseline covariate, only few are statistically significant. If you look at the p-value, so this is the alcohol misuse, was significant, APOE genotype was significant, as well as family history was significant. And also the red line shows how the longitudinal MMSE predict the risk of conversion to Alzheimer's disease. And you can see this is very strongly predictive of Alzheimer's disease based on the joint model. So these results are very similar to Cox model, as I said, but this is jointly modeled with longitudinal information, and MMSE is a time-dependent variable in this model. And then I computed the boots. I have taken 500 bootstrap sample and computed Optimism corrected dynamic AUC for both model actually. So idea of the Optimism correction is that most of you may know who are in machine learning that people use cross validation. The reason is that if you feed the model on a data set and evaluate performance on the same data, you overestimate the performance. And this is the point of actually Optimism correction. So if you feed a model to the original data and compute dynamic AUC, so this original dynamic AUC will be optimistic because you are fitting the model and evaluating performance on the same data. And same here, if you take 500 bootstrap sample and calculate dynamic AUC on each of them, then this also gives kind of optimistic estimate because you are using the same data set for fitting the model and evaluating the performance. So idea of the Optimism correction is that you calculate dynamic AUC, you feed the model on the bootstrap sample and then evaluate performance on the original data, right? So difference between this and that will be amount of optimism. So feed the model to the each bootstrap sample and use them to calculate performance on the original data. So this gives an amount of optimism actually. So dynamic AUC B boot. So this means on the same data, this is optimistic performance. And this is not optimistic because you are using different data. So fitting the model on the bootstrap sample, but evaluating performance on the original data. So you take the average of this difference. So this gives a measure of optimism. And you take away that optimism from the original dynamic AUC. So this is how actually you calculate Optimism corrected measure of performance. So I have done it for dynamic AUC as well as prediction error for both type of actually model, joint model and landmark analysis. And here you can see the results from the simulation based on the 500 bootstrap sample from the ADNI data. So dynamic AUC and the prediction error compared at 4 landmark points. So I've considered half-year interval actually. So 4 landmark points, 1 year, 1.5, 2 years, and 2.5 years. And I have considered a time horizon of 2 years because this is a small data has over 9-year duration. So it is not possible to calculate, say, 5-year time horizon. So for this particular data set, so I have considered a small time horizon. Prediction window is 2 years. So you can see dynamic AUC for the joint model, first line, and the second line is for the landmarking based on Cox regression model. You can see measures are pretty similar actually. So the numbers differ only in the second place, actually decimal place. But both method is doing very well actually in terms of calibration, discrimination measure. So this is dynamic AUC. So you can see that if you compare these numbers, the joint model has performed slightly better than the landmarking approach for all of the kind of time point, landmark time point. And for the prediction error, the smaller is better actually. There would be a decimal point here. Actually, I forgot. This is a typo. So you can see that again, joint model has done slightly better, except for the last kind of landmark, all 3 landmark point. The prediction error for the joint model is slightly higher than the landmarking. No, I think prediction error is lower for the joint model than landmarking approach. So to summarize, that joint model performs slightly better than the landmark approach, but the magnitude of kind of gain is very small. And this is just a summary and the plot of the sort of simulation results, just to compare visually. So the green line, so the blue line shows the landmarking. This is dynamic AUC, area under the curve, and the red line is the joint model, and blue line is the landmarking approach. So you can see in terms of dynamic AUC, the red line is kind of doing the joint model is doing slightly better than the landmarking approach, except for the kind of last landmark time point. And this is the same in terms of prediction error. So prediction error is smaller is better. So again, the joint model is doing slightly better than the landmarking approach, except for the last landmark time point. So actually in this, although you can see very little data here actually, so 500 bootstrap sample took ages on high performance using parallel computing, because fitting joint model on 500 data set and doing dynamic prediction is very highly computation intensive. But in terms of gain actually, it is not that much gain. So people may consider whether you need to fit a kind of complex joint model, because landmark approach seem to be doing very close, have the very close performance. And I have to say that this landmarking approach I have used is the very basic one. So it just doesn't do any interpolation of the longitudinal marker. So it just do last observation carried forward and then applying landmark approach. And just I would like to thank the medical school for funding some of the work that I've done. And one of the PhD students from Queen Mary University has currently based in the University of Dhaka has done some work for this. And I'm grateful to the Alzheimer's disease neuroimaging study for providing the data. And that's all I wanted to talk about. Actually, I'll be happy to try answering some questions.
Thanks very much, Mizan, for this very nice introduction to the topic, and it was really informative and very interesting. So yes, let's open this question time now. So if anyone has any questions, please just raise your hand, or you can also type it in the chat, and I'll be happy to read it for you. So any questions for Mizan?
Hello, please. I do have a question.
Yes,
yeah,
sure. So you used the whole data set, the original data set in your bootstraps to assess the performance of each models. I was a bit surprised you would use the whole data set, the original data set, and not only the slice of the data set which were not used to fit each sample for each bootstrap.
No, obviously so I have used the same because bootstrap data. So I simulated 500 bootstrap sample, right?
Yes.
So for fitting the joint model on each of the bootstrap, you have to use the whole data set. But for a landmarking approach using Cox model, obviously you have to exclude data. So it is not for landmarking, it is not fitting on the whole data. So based on the for a particular landmark, you have to use data for only people who are at risk at that particular landmark.
Sorry, I meant, like, for example, if you have 100 observations, each bootstrap, each sample you will select in average 66%. And when are you going to measure the performance of your model on the 100 people or the 30 people for who you didn't use data to fit the model?
All right, I understand what you mean actually. So out of bag error, you are referring to out of bag error calculation.
Yes,
this is what is done in machine learning actually, but optimism correction is a bit slightly different concept. So so optimism correction is, so if you feed the model on a bootstrap sample, you feed the model on a bootstrap sample, right?
Yes.
And make the prediction on the bootstrap as well. So it will be opportunistic because you are using the same data, right? So you do that, you do it twice, and then you feed the model on a bootstrap sample, and then evaluate performance on the original data. So it's a different data set. So only 66% is common.
Okay.
So this difference gives you a kind of amount of optimism.
I see.
So it is a slightly different from the out-of-bag error. Yeah,
Okay.
Most of the machine learning method is actually out-of-bag error.
Okay, thank you for your explanation.
Yeah.
And great presentation.
Yeah, thank you.
Thank you. There is another question from the chat. It's from Ralph Akia. Sorry for my pronunciation if that's wrong. So the question is, you indicated it's computationally difficult or impossible to model multiple biomarkers for the longitudinal submodeling. Could you, however, have multiple biomarkers as time-varying covariates?
Yeah, you can obviously feed a kind of time-varying Cox model, obviously, but sometimes for some of in the MMSE example I mentioned actually, sometimes they call it endogenous covariate. If the covariate is so in case of dementia, for example, people are not sure whether actually the dementia affect MMSE or the MMSE affect dementia because it's a two-way process. It's called endogenous covariates. So because we don't know whether which predict what actually. So it may be that if people get dementia, then they get lower. Their cognition is affected by, because they start to have the disease. That's why actually their cognition is kind of lower. Or other people can say, well, my cognition is getting worse, and I'm likely to get kind of dementia. So it's a kind of both directional. Effect can be both directional. So that's why sometimes we call it endogenous covariate, because in this situation, it is actually not recommended to feed a kind of standard time-dependent Cox model, because the effect can be, you cannot ascertain which predict what. So MMSE can predict your dementia, or dementia can predict your cognition. Just 1 minute, actually, I have to.
Oh, I think Mizan had to go for some reason. I hope he will be back soon. There are still a couple of questions in the chat. Actually, I do have another question, so let's hope that Mizan is back. Let's hope he's doing well. Oh, are you okay, Mizan?
Yeah, someone knocked my door. Actually, my son came from the school. I just to
okay.
answer the door.
You can, don't worry. It might happen to me now as well, so don't worry.
Yeah, this is one of the adventures of having doing homework, working from home.
Exactly.
Yeah, so
but the funny thing.
Yeah, so
anyway,
so answer is yes. Obviously, you can do fit time-dependent Cox model, but for some of the covariate, the example I have given, actually they are called endogenous covariates. So it is not recommended to use kind of. So if you use time-dependent Cox model, you have to assume that causal direction, right? Your MMSE affect Alzheimer's, but it can be other way around. Your actually Alzheimer's affect your cognition. So that's why it's a joint model is a more appropriate, because you don't assume a causal direction for this model.
Thank you, Mizan. just for the people that are not maybe looking at the chat, you can find there the classic paper about optimism correction that Professor Daniel Stoll is sharing there for all of us. So thanks very much, Daniel, for this. There is another question about how long did it take the bootstrapping? When you said that it took ages, someone is saying that we should be minimizing the computation burden and sampling time. And how long did it take for you that?
Yeah, because I did it kind of serial computing in a kind of cluster. So for 100, I initially did a kind of 10 simulation on my personal computer, which I was able to do in my personal computer. So for 10 simulation, it took, say, a couple of days. So I thought I have to do, if I had to do kind of 500 on my personal computer, so it could be a kind of month or so. so that's why I decided to use a personal cluster computer. So you can see that in terms of performance gain, it is not that huge fitting a joint model. So that's why if it is a kind of simple application with a kind of 1 or 2 biomarker, the Cox landmarking can be good enough actually than joint model, although the joint model is a more methodologically sound. But software are improving actually. So when I did the computation, actually, I'm not sure I had all the software because all the data, because the joint model is kind of relatively new method. So, but I see the improvement in the computation procedure. So maybe in future, it may be feasible to do more kind of demanding computation. So it's improved, the situation is improved more or less.
Okay, thanks, Mizan. I can't see any other question. Now there are like 4 minutes to go, and I have a very quick question. I was just thinking in the kind of data coming from clinical trials that we are very used to be analyzing. And most of the time that we do have is discrete. So we do have discrete time points with some measures on each time point, right? And we use longitudinal models. And I was just thinking how these models that you were presenting could be used for time discrete points and measurements. Can they be used for that?
Yeah, so if you collect longitudinal data, they're always collected as discrete, right? You don't take continuous measurement. Like if you take blood pressure, say every few weeks, so data that you collect is going to be discrete anyway, even if you're measuring continuous variables. So I'm not sure, is that what you mean by discrete data, or it's a kind of...
Well, I was thinking that, for example, measurements that you just have for 12 weeks, and you have one measure for each week, and I wouldn't, you see.
Yeah. So it will be perfectly okay to fit a kind of either joint model or use a landmarking approach for dynamic prediction. So only thing advantage of joint model is that it will give you a smooth version. So if your data are discrete, observation will be scattered, right?
Exactly.
But if you fit a joint model, actually, joint model will use the smooth version of the trajectory for predicting the time to event outcome. So it will interpolate actually the data. So which is not done by if you use the standard kind of landmarking approach. So this is the basic difference.
Okay. Yeah. Thanks very much. Okay. Is there any other comment question? Mian, maybe you want to ask yourself this question, or would you like me to read it again?
Yes, thank you. Sir, I have a question regarding the subsampling. So as I asked previously about the time, so you said that it takes a lot of time, and if we have a large data, so it takes time in months too. So if it takes very much time, how can we say it a good or accurate model? And in another, my question or answer to my question is, can we consider a non-Newton subsampling for as a sampling method? And which method can we use for what we say for let them, but if possible, kindly answer me this. Thank you.
Yeah, so in terms of the computing time I mentioned, it is based on, because I'm doing simulation, right? I have evaluated the model on 500 data set, but in a real application, you are not fitting a model on 500 data sets. So if you apply this technique, rather than, because my study was a kind of comparison, so I've done lots of data set, but if you do a dynamic prediction, it will be only one estimate based on a one particular data set. So this is still feasible actually if you have a kind of big enough data, but it is still available with the availability of software nowadays. You can still fit a joint model. I'm not sure what you mean by accuracy actually, because the simulation, bootstrap simulation, give an average over multiple repeated sample. Obviously there will be error, but on average actually the prediction performance should be quite actually close to the true prediction error, because it's based on averaging over a large number of simulated data. Right. So although the computation is difficult for simulation type studies, but in practical application you will be using a method for a one data set. So I don't think computational burden is a huge issue unless you have a loss of biomarker. So if you do a prediction with say 10 longitudinal biomarker, then it can be difficult to fit a joint model because dimension is huge, numerical integration dimension. But
Okay.
otherwise, I think it is still fine. So others,
Okay.
Can you remind me which is the other simulation method you mentioned?
Non-Newton sampling.
All right. Okay. So I'm not familiar with the simulation method that you mentioned.
Okay,
actually.
this Bayesian is an updated Bayesian methodology. So many yes, what you told about a student from Queensland University or something about who is now in Dhaka University. Someone did work on non-Newton sampling, subsampling in Queensland University, and one or two others are working in Sweden too. So that's why I ask about that. Can we consider that this subsampling? So, but however, it's a very good answer. Thank you very much. Thank you.
All right. Okay. So I'm not particularly familiar with the simulation that you mentioned, but yeah, maybe I need to have a look here. It would be good if you kind of send a link to the chat, a reference to the chat. Yeah.
I don't have right now, but I will share it with
All
Dr.
right. Okay.
Raquel, with Dr. Raquel, and she will share it with you. Thank you.
All right,
Thank you. Thank you very much. Thanks, Mian. So
Pleasure.
We are 2 minutes now over 4, but there is a last question. I don't know, Mizan, if you have time to answer it, and this would be the last question that we.
Yeah, it's
okay.
fine for me. Yeah.
Okay, yeah. So ThinkWalk is asking, can you apply dynamic modeling approaches, the ones that you suggested, but on binary outcomes rather than time to event outcome? Thank you.
Yeah, so if you want to use it for that binary outcome, so I suppose you mean binary longitudinal measure, right? So it is doable, but the linear mixed model will be a generalized linear mixed model. Right? So only difference is that the longitudinal model will be a generalized linear mixed model like logistic model, and you can still use joint modeling.
Great.
It is possible.
This is answering your question. Okay. Yes. Thank you. So that's everything then. Well, thanks very much, Mizan, for the talk, for the nice discussion. And
all right.
back with us today. Thanks very much.
Yeah.
You can go with your son already.
No problem. I was a little worried because it's a bit a theoretical thing, because it would be nice to have a nice clinical application, but because of the time limit, actually, I couldn't kind of fit in. But I thought it was kind of useful given an overview of the simulation study.
I think that as an overview was very interesting anyway. I'm sure about that for everyone.
All right.
Thanks very much.
And
I think the people
like,
are
it would
in
be
the chat
great.
as well.
It would be great if you could include me in the kind of mailing list, because I don't seem like I'm getting email about all these seminars.
No, you should be getting it. I will check my list, but you should be there from years ago. So maybe
all right.
maybe just I don't know. I will double check. Thanks, Mizan.
Yeah.
And thanks everyone for attending. And so we will be now confirming our next seminar for July, and we will be informing through our usual channels and Twitter, and also by email to all of you. So we hope to see you by the end of July again here in these seminars. Thanks very much, and enjoy your evening. Thanks everyone.
Right.
See you soon.
Bye.
Bye. Thank you.
Listen, do we have some time?
Yeah, sure.
Yeah, just.